We're continuing our Chapter 7 notes. We'll discuss impulse, we'll talk about different types of collisions, and continue talking about conservation of momentum. So first, when objects collide, they are deformed due to the forces. This is important for a couple reasons. One, it helps explain what happens to the energy. So a lot of that kinetic energy gets turned into elastic potential energy during the collision. And two, it tells us that the collision occurs over some length of time, right? It's not sort of an instantaneous collision. So that change in momentum for the tennis ball here pictured is going to depend on the magnitude of the force and the duration of the force. Remember, the force will affect the acceleration, but the final speed will depend on how long it's accelerating. So same concept. This equation is on the equation sheet. Keep in mind, this equation technically includes net force, but it doesn't show that sigma Greek letter. It just says F, but F really should be net force. And that right side of the equation, is referred to as impulse. So force times that duration of time is impulse. Sometimes impulse is given a letter J, capital J. That is not always used, though. Sometimes impulse will just be referred to as force times time. Units for impulse are newtons times seconds. Keep in mind that's equivalent to the units for momentum, right? Since it's equal to change in momentum. So you could write it as kilograms times meters per second. But if we're talking about impulse, generally it would be better to use newtons times seconds. For most collisions, the time of collision is very short. And so we're going to do some estimation to make this calculation simpler. So force times time, if we're looking at a force versus time graph, that means we can use the area under the curve to find that product. But again, since we have this kind of weird curved shape, we're going to estimate it. And the way we're going to estimate it is just to take the average force, or about half of that peak force. And you can think of this as similar, like it'd be the same thing as if you pretend that is just a triangle. And so if we did 1/2 base times height, that's the same thing as that green shaded rectangle area, which is essentially 1/2 height times the base. The same impulse can be achieved through having a larger force over a shorter time duration, or a smaller force over a longer time duration. So a lot of times if we want to think about minimizing force, what we want to do is extend the time that force is applied. So one way this can be achieved with cars is by turning the front of the car into what they call a crumple zone. So the front of the car is meant to crumple up because by doing this, it means that the collision lasts longer. So if you have an accident, cars today are designed to total more easily. And all of that is just to protect the occupants in the car. So your car is less likely to survive the accident, but you are much more likely to survive. Here we have an example for impulse. So pause and resume when you're ready. So for part A, we're finding impulse. So impulse is capital J, or force times time. It's also equal to the change in momentum, or mass times change in velocity. For this problem, we know mass and we know change in velocity, so we're going to calculate it that way. And we get negative 540 newtons times seconds. Negative because it's a decrease in momentum when he's coming to a stop. A positive impulse would tell you that momentum is increasing. For B, we're trying to find the force. This part is a little unclear which force, if we're finding net force or the normal force. because you get different answers. So I'll show you kind of both. So we have our impulse, force times delta t, equals mass times change in velocity. For the velocity, I'm looking at the average velocity being the distance over the change in time. And this average velocity is the 7.7. That's his speed when he starts to come to a stop, plus 0, and then divided by 2. So I'm just very quickly finding the average. You could use one of the accelerated motion equations, by the way, to solve for this, but I thought it was easier to use this simple one. So I'm finding the average by doing the initial speed, the final speed, and then dividing by 2. For the distance, it says he moves 50 centimeters, so change that to 0.5 meters, and we can solve and get our delta t as 0.13 seconds. And then if I plug that into the equation, I get a force of 4,190. That force is the net force. So if I wanted to know specifically how much force the ground is exerting on him, I'm really going to solve for normal force. So I'd plug in 4,190 for the net force. You'd end up, adding gravity, the force of gravity, to both sides. So the normal force is even larger, right? Because it has to not only equal gravity, but surpass the force of gravity in order to slow him down. So we'd get 4,870 if we want to know the normal force. So collisions are often divided into two categories, elastic and inelastic. Momentum is conserved for both of these types of collisions, which is very important. So momentum is conserved regardless of what type of collision is occurring. If it's an elastic collision, then kinetic energy is also conserved. Trying to use conservation of kinetic energy is not super helpful, though, because the equation, it has the 1/2 in the square, so it's harder to use than conservation of momentum. So typically we, just stick with conservation of momentum for these collisions. We can derive another equation, a simpler one with elastic collisions, and I'll show you that later. In reality, there's no such thing as a perfectly elastic collision. Usually when things collide, always when things collide, there's some loss of energy in that process. So that means it's inelastic. So an elastic collision would be they collide, no energy is lost, and they still have all that kinetic energy at the end. Inelastic, when they collide, some of their energy gets turned into heat, and so there's less kinetic energy after. Objects that stick together, that type of collision may be called like completely inelastic or perfectly inelastic. It doesn't mean that they lose all of their kinetic energy. It just means that they stick to each other. So they move off as one object. And if it's a partially inelastic, that means they're not sticking together, but there is still some loss of kinetic energy. And one other sort of scenario, it's not generally considered a type of collision, but it does still work with conservation of momentum, are explosions. So this is any scenario where you have, one object that breaks apart into two objects. So this could be, the rocket that was expelling fuel out the back. This could be someone who, throws some heavy medicine ball forward. So they start off as kind of one object, and then they separate into two. So I mentioned before, with elastic collisions, it's momentum conserved and kinetic energy is conserved. This is the only type of collision where kinetic energy is conserved. Trying to use, 1/2 mv squared plus 1/2 mv squared is not super helpful. But we can actually derive the equation shown there from that conservation of kinetic energy and momentum. And this one is really useful. It's not on the equation sheet. I don't think you'd be expected to use this equation on the AP exam. but it could potentially be helpful for multiple choice problems on AP exams. And really the best thing about it is it is so simple, right? So the difference in their speeds before equals the inverse difference in their speeds after. So helpful equation to use. Here we have our first elastic collision example. Go ahead and pause and resume when you're ready. So we have two billiard balls of equal mass. Ball A is moving with speed v, ball B is at rest, and then we're trying to figure out how fast they're going after. Since we don't know either of their speeds, we're going to have to use two different equations, which means we'll have to use both conservation of momentum and that sort of a simplified version of conservation of kinetic energy, that the difference in speeds before is the negative difference in their speeds after. So conservation of momentum, I'm just plugging in the values given. So both have a mass of m. A is going with speed v before, and billiard ball B is not moving, so it has zero momentum. Afterward, we don't know either of their speeds, so I'm leaving that as VA prime and VB prime for now. And since all have the same mass, I can cancel out m from each of the terms. Next, I'm going to use that simplified version of a conservation of kinetic energy and plugging in the same values that are known. I know VB initially is 0, right? It starts off at rest, so I have this kind of simplified version. So if you notice, we have two equations. That left side, that V is kind of a known value, but the right side, the VA prime, VB prime, those are still unknown to us. So I'm going to have to combine these equations to solve for the unknowns. So one way you could do this is adding the two equations. At this point, we have a basic system of equations. There's a lot of different ways you can solve, so follow whichever method you want. You could set them equal to each other. You can add and subtract equations, whatever method you prefer. And I can get that VB prime is V. So that billiard ball that was at rest is now moving with the speed that billiard ball A was moving with before the collision. And that means VA prime is at rest. So their speeds have essentially just switched. Here we have a second example problem. This time it's actually giving us values, so maybe you'll find this one easier. So pause and resume when you're ready. So we're finding the velocity and mass of the target ball. That means, again, there's two unknowns, and I'm going to have to use both of those expressions. If these problems gave us everything except one unknown value, we could just use conservation of momentum. Most likely that's how you would solve that. All right, so I have my first equation. I'm going to plug in the values. Again, this shows you how nice the equation can be to use. When you know 3 of the speeds, it's easy to solve for the 4th. So right away, I get the velocity, the new velocity of this target ball as 4.8 meters per second. And I can use conservation of momentum then to solve for mass. And I get a mass of 0.56 kilograms. Our last example problem today is an example of an inelastic collision. Go ahead and pause and resume when you're ready. So this is a common problem in physics because it brings together two different kind of topics or fields. So first, it's clear we have a collision going on, and this is a perfectly inelastic collision because they stick together. So I'm just using conservation of momentum. Before the collision, it's just the bullet that has momentum, so m times v. After the collision, they stick together, so I kind of literally have stuck together the two masses inside parentheses, so I have their total mass times some new velocity. and I've just solved for that new velocity. Next, from that point on, if we're looking down at part B of this diagram, after the collision, this is essentially a pendulum. So it starts off with some speed, right? It's moving, and then it swings up to some height. And so we have to go back to our last chapter and look at conservation of energy. So we start off with kinetic energy, 1/2 mv prime squared. That mass, by the way, that's not just m for the bullet. I'm just trying to use like the basic equation for kinetic energy and set that equal to mgh. Again, that's kind of our basic equation for gravitational potential energy. If you notice, though, the mass cancels out, so I don't even need to worry about substituting in, lowercase m plus capital M, because whatever the mass is, it cancels. And again, I can solve for v prime. I get root 2gh. And then I'm setting those two expressions equal to each other. So mv over m plus m equals root 2gh. And then I'm solving for v. And I get an expression, a little long.